not just the security, but all the fun things you can do with binary analysis. And the idea of binary analysis is we're going to gather information about what a program does from the binary alone. We're not going to need source code. And the goal is to gather as much knowledge about what that program does as you would have if you had the source code. And once you can do that, binary equals source, and it's all open source. So why would we want to do this? Well, one thing is proprietary software. The people who sell it rely on the fact that you don't know what the program's doing. So there's obscurity there. Unless there's a way of telling what the program is doing from the binary, they have security by obscurity. They also do all kinds of things with that program that they might necessarily want you to know how to do.
They need to get these lights too, though. They
DRM
all sagged.
licensing schemes come to mind, but things like spyware, a lot of nasty stuff happening on programs, and all that stuff is distributed by binary, of course. Another nice thing to do with binary analysis is see if someone has stolen your source code. If they've stolen your source code and put it in your program, put in their program, it's typically very difficult without sophisticated tools to figure out that your algorithm, your routine is in someone else's program. So if someone is taking GPL code and putting it in their software, it's relatively difficult to figure that out. With binary analysis, we can do it fairly quickly. Then, of course, there's a security vulnerability problem. How do you audit a binary? Very, very difficult to do manually, tracing through with the debugger. You have a binary analysis tool which can basically convert that program into a model which is similar to the source code with the same amount of knowledge of the source code. Now you can start auditing that for security vulnerabilities. So you can take a binary and do the same things you can do in a source code audit. Another reason you'd want to do binary analysis is some stuff really has to be in a binary, and those are your things like your compiler. You need a compiler to build a compiler. You need a compiler to build other code. How do you know what that compiler is doing? It's a difficult problem. Compiler is probably the most interesting program to backdoor, which Ken Thompson did in the early 80s. He wrote a paper in 1985, Reflections on Trusting Trust, to talk about what he did. What he did was, he wanted to backdoor the login program for Unix. But instead of just modifying the source code for the login program, which he thought would be detected rather easily, what he did was he modified the source code to the compiler, so whenever it saw the login program being compiled, it would insert a backdoor into the login program. He did this ostensibly because he was sick of system administrators asking him questions, and he wanted to just log into their systems and fix the problems. Ostensibly, that was his reasoning. So I guess Ken Thompson was a hacker too, of course. So what he did was he modified the compiler to put the backdoor in, and then he compiled that, and then he distributed the binary compiler. So without binary analysis, there's no way to find this backdoor on your system. It's a very interesting paper. I highly recommend it. So now I'm going to hand it over to Joe Dog here, and he's going to go into some of the more technical details of what's going on behind the scenes here.
Okay. Hello.
Thank you.
So, binary analysis is typically a process that, until recently has been done very much by hand with disassemblers, with tools like hex editors. Someone who's done a lot of vulnerability finding and exploit generation, and generally has gotten to the point, where you can, open up a program with a tool like IDA Pro or GDB, search for an instance of a problem, such as, you know, you find like an sprintf or something, and hone in on that, and you know, do the actual manual looking at it and like trying to trace it back to a place where maybe you might be able to get a variable into a certain place or whatever, and you know, trace that all the way through to the point of exploit. That process is something that human beings do that can be automated enough with tools such that you don't actually need to you know, do it all by hand. It can take hours and hours and hours of poring over hex dumps and disassembling things. If, for example, all of the data flow of a program, which is the map of sort of all the definitions of variables to all the uses of those variables, if you were to have that map already available, there would be no time spent tracing. You would just, you know, walk the graph and say, oh, here, this is possible. In fact, you could do that with a script. You could, you know, write a script that queried these graphs. Now, of course, the generation of the graphs is a hard problem, but it's not intractable. If anyone has ever, in the audience here, has ever built a compiler of any sort, then you're probably familiar with the concepts of data flow and control flow, which are two parallel things that make a computer program go. If you have the source code, you generate these intermediate representations and then convert that into a binary. What we've done over the last 3 or 4 years is develop a tool which could be thought of as a decompiler. And it builds those same models from binaries and could, if you wanted, export source code from that. Sure, go ahead. So basically there's like 4 parts of the system that does this. And they're related to compiler construction, but we've taken the different tack of starting with the binaries. So we have a front end that works much like a disassembler, but disassembles to an intermediate language, a representation that's transformable. You have a transformable entity, you know, that represents, you know, very low-level instructions like calls and conditional jumps and things like that. And you also have high-level constructs in the same language, things like for loops and procedure calls that are expressions that have return values and parameters and variables. All those high-level concepts are all present in the same language. And then you write a set of transforms that get you from the low level to the high level representation. We start off, you know, feeding in any debug symbols that we happen to have, if you happen to have those, which makes your life a lot easier. It gives you some type information so you don't have to reconstruct it. And then you go into a data flow transformer, which it basically undoes the register coloring problem. Building and reconstructing variable lifetimes is sort of a key process. You want to make as many variables as possible and merge them together to form this data flow graph. Because eventually, you know, when you're done with this process, you have a whole series of variables with non-overlapping lifetimes that represent the flow of, you know, the sort of maximal flow of data in the system. Once you have that, what you have is almost readable once you've done this process, and that feeds directly into a control flow transformer. A control flow transformer looks at things like an unconditional jump, or a condition, you know, that jumps to the, you know, the head of a loop with a conditional jump at the top that jumps to the end, and finds constructs like that. If anyone is interested in program transformation, that's you know, a commonly analyzed computer science concept that is really applicable in this area. So, you know, it does things like interval analysis and regenerates high-level control flow for things like loops, conditional two-way, three-way, n-way conditionals, and virtual function calls, things like that. And then once you've done that, you know, you have these high-level semantics in this intermediate language, which just need to be exported in a language that's readable. Pick one. For the most part, semantics are the same from language to language. Some languages can express certain concepts better than others. For example, some languages can do multi-level exits. Like in C, if you program in C, you know that there's a break statement, and that breaks you out of the current level of the loop that you're in. You can't say break 2 and break out of 2 levels of loop, though. You actually have to use a break and then another, like maybe a Boolean, followed by another break, in order to actually do that construct. Some languages actually have break 2, for example, and you can represent and transform those concepts. Like, note that to add break 2 to C, all I have to do is introduce a Boolean in order to do that. There's a certain transformability that lets you say, if I want to add a control flow construct, I can do so by adding a data flow construct in its place if I have the accessibility to do that. Some languages can do go-tos, some can't. There are certain classes of language, as long as your intermediate form can represent all of the different types of control flow and data flow, then you can analyze everything from C to Java to C# to C++ to whatever. Arbitrary output language is generally called resourceable, and arbitrary input binary would be called retargetable. So what we've done is we've built a retargetable resourceable decompiler that generates high-level models and control flow using a few different techniques. Once you've got a model, you can do interprocedural analysis. This is something that humans are generally pretty bad at, but computers can be very good at. The notion that you can create a variable lifetime by saying something like new a class or something. We store some data in it. And then several procedures later or deeper in the tree, we use that data. Generally, humans take a very, very long time to track that kind of data flow. But, to a computer, it's just looking at the graph, so it's something that we should be delegating more of, so we don't have to spend our brain cells doing. It's just simply that we lack, until recently, we've lacked good tools to do this kind of work. The other thing that this model affords you once you've built it is the ability to ask arbitrary questions of it. You can, right now I could say, right-click on a variable, as you see it, and ask the question, what possible values does this variable have at this point? And what possible control flow paths get me from point A to point B in the code? And what are the constraints on the data flow in order to do that? Those kinds of questions are exceptionally valuable. We ask ourselves those questions when we're writing exploits because that tells you whether or not the program or the vulnerability that you found is actually a problem or not. Can I get there from here? If I have tainted data input coming in off the command line or off of a network packet, does it actually make it to the bad string copy? Being able to traverse the graph and just answer that question is, in record time, sort of a great equalizer for those of us that are hunting things. I don't know. Let's see. Once you've built a graph, certain things just completely fall out. You can say, does this thing use the network? If this program that you've written that shouldn't be using the network and it does, it just kind of sticks out. You'd see all the different calls to the different functions. It would call system, and you're like, okay, it shouldn't be calling system. Basically building a program profile and comparing against that is the first and very simple thing you can do. Much more complex scripts can be built, though, that do things from data tainting to range propagation to, just basically figuring out, sort of automating the process of exploit generation, finding all the hotspots, propagating danger, coming up with an abstraction for what's dangerous in a program and propagating that throughout the entire thing. These are constructs that are much easier to do with a tool than humans, no matter how good you are at it. Sure. I'm going to turn it back over to Will here.
Just for an example of a script that you might write once you have this model, a very common problem with web applications is something called SQL injection. And what you can do is you can codify in a set of rules what causes a SQL injection problem in a program. So we would write a script and it would look something like this. We'd say, what are all the function calls that a program can do that call out to a SQL library? So things like ODBC calls. In Java, you'd have a call execute query. So you build a list of all the functions that basically are, quote, dangerous, right? Because, unless the data going into this call is trusted, has been validated, and you know what it is, you're going to have a SQL injection problem. So you build up that list of function calls, and on the other, you build up a second list, and the second list is all the ways that input comes into your program. So, reading stuff out of, an HTTP request, the APIs for doing that, or just reading data directly from the socket, or reading data from standard input. And you build up this other list of all these functions that pull input into your program. Then what you do is you use the data flow, and for all those dangerous SQL calls, you follow the data flow back and see if any of that data, any data, a few bytes of it, whatever, if any of it came from those untrusted sources, it has to pass through a validator function to make sure that the data is known, or you have a SQL injection vulnerability. So if it's something like Java, you're using the struts framework. There's a very clear structural way of doing validation. And what we can do is we can follow the data flows and see if you're passing through a validator function, or if it's just arbitrary, sort of arbitrary C code. You can flag where your validator functions are, and we can look at all the different data flow paths and quickly tell you if there's some path that gets from, basically untrusted to something which needed to be trusted very, very quickly. And the power of automating this stuff with scripts is, sure, a human could do this, and a human does a really good job, but the problem with the human is the human does a really bad job of looking at 100 different cases, because humans make mistakes. And I don't know if any of you have ever done code review, but, after 8 hours, you might miss one of those 100 cases. And then there might be some other guy who's got a binary analysis program who runs it through and finds the one case that you missed. So the beauty of the automated approach really is the consistency and the repeatability of the analysis. That if it knows how to find one class of problem, it'll always find that class of problems. It's certainly not going to find all problems you could have in a program. Some things are very difficult to find in an automated way. But a huge amount of the vulnerabilities that are major vulnerabilities out there, things like buffer overflows, format string problems, integer overflows, SQL injection, cross-site scripting, things like path traversal. These types of problems are very well known, well defined, and they don't rely on understanding the design of the program, what the program is doing. They're just very structural problems which can be defined with a set of rules, and the model can just be scanned with that set of rules.
In terms of automation, before we move on, I also wanted to point out that typically breaking into stuff is an any path problem. You only need one vulnerability that's exploitable to break into something. But security is very much sort of an all paths problem. You need to secure just about everything, because if you leave one hole, that's the one they're going to break in. there's sort of an order of magnitude difference there that makes the life of the person breaking in a lot easier than the person trying to secure the program. Tools that are automated sort of level the playing field a little bit by allowing people to find every instance of a problem and address it. Whether they actually get around to addressing it is more of a political problem, but you need sort of this robotic exoskeleton to be able to deal with the problem. If everyone's got an automated tool, then finding one problem versus finding all problems happens at the same rate. So that's a big boon for people trying to fix stuff. Let's see what we have here. Well, I can point at this. This is not an amazingly accurate analysis at this point, but it's something we can poke at. I don't even know where this came from. This came from what, Apache? Some library?
It's a support library for Apache.
Yeah. There's Apache for Windows has this function called true random in it, and it sits inside some DLL. If I'm remembering correctly, we didn't have source code to that.
Right.
Right. It's actually something that you don't have source code to, which is kind of weird.
You
You can get it, but it doesn't come with the actual tar of everything. So we fed it into this, and what you're seeing here, it doesn't look like a human-written C or C++, but it doesn't need to be, because it's just the computer that's got to understand it for the most part. Internally, there's a graph sort of representation that you really can't see here, but this is sort of the generated source. We take the program, we feed it into this tool, which we wrote called Smart Risk Analyzer. You feed this in, it runs, it chunks for 4 or 5 hours on an executable, produces these graphs and lets you run scripts off of the scans menu there. You can see that there's a little tag at the bottom, a little warning thing, and it's pointing out that srand is being seeded with something that is effectively constant, which really doesn't make for true random numbers terribly well. But you wouldn't know that if you didn't have the source code, which we didn't have, but we found the problem anyway. That's sort of the point, is you don't always have the source, but you really do want to, if there's, let's say somebody messes up and instead of using like a left shift, they use just a less than sign or something in their code. And that caused a completely different semantic to happen. Then, you might not notice looking at the source because it's, it's passable, because it looks like any other thing. But the problem may escape human attention, but it won't escape a script. A very, very good example of this recently was in the Linux kernel. Anyone caught the vulnerability where someone had actually removed a single character during a check-in from the vfork call. Basically said, if UID equals 0, then blah, blah, blah. Except that it wasn't double equals, so they took out one of them. So that if you called vfork, it set your UID to 0. Again, could be, plausibly deniable, and definitely escapes people's attention for a while. But wouldn't escape the attention of a script because it's not looking at the source, it doesn't care, it just wants to know what the program does. Insofar that compilation could be viewed as encryption, that the CPU could be considered a decryption device in the same context. The idea is basically, all your semantics have to eventually meet the CPU if, you've written them. So going from the binary standpoint is the only way to be sure that you're analyzing what the CPU is actually going to be running. That's the tack that we took. There's a lot of source scanners out there, but there are very few effective binary scanners out there. This is one of them. There are other tools which purport to do that kind of work. IDA Pro is very good at producing disassembled output, and combined with some scripts that are publicly available, can do certain types of data flow analysis. It's not quite as automated as this, but it's very, very good if anyone wants to play around with this stuff. I only say that because this program is not currently available for download. It's not free, and it consumed about 4 years of my life in order to make it. So eventually the technology will get out there, but it's not quite there yet. So give another couple of months, and you're going to be hearing more and more about this kind of stuff. In theory, we could actually do it live here. Hold on. Do you want to? Oh, this is actually the program itself. I fed in Microsoft binary into it. Did you know that you have not source code, but you have symbols that you can download for everything that they publish? So for the most part, binary plus symbols is pretty close to equivalent to source code once you feed it in through something like this. What I did is I fed in the AVI file decoder because it's small and I didn't have that much time before this talk. Anything huge usually takes 24 hours to analyze. It's just a really process-intensive task. Decompilation is a much more intensive process than compilation because you're reconstructing stuff, not throwing it away. But yeah, so I fed this in there because AVI files are opened automatically by Internet Explorer, which makes this, any holes found in it, chances are they're remote, and you can do it through email. So yeah, we poked at it, and you can see there that we've generated some stuff for like AVI build filter. If there's stuff inside, this is for creating and reading back AVI files. There's a local alloc that it does, which it then passes interprocedurally to something else. And it's just noting, that this is potentially the start of a data flow. The analysis scripts that we have in there right now are not too deep, but it's noting that this is the start of a 64-byte chunk that could possibly be overwritten later, so it marks it as a possible error. It also went through and marked all the different calls to sprintf, which are in the AVI file decoder, which, they're down there. Yeah, so you can see it as printing into a buffer and, querying some value out of the registry. All of this stuff, for the most part, is stuff that you could, in theory, see with a disassembler, but makes a lot more sense if you can just kind of click through it with a tool like this. It's a lot faster. So no, I would actually just feed some programs and wouldn't let you look at it, but you'd actually be sitting here all night. It's not terribly amusing. It sits there, and the progress bar doesn't move for a very long time. Just wanted to show you that it's real. That it works. So I'm actually going to hand it over to him again so he can talk about other uses of this kind of technology, including differential binary analysis and what use that is to the world.
So a particularly interesting use of binary analysis would be to be able to just look at two versions of a program and see what changed. So one interesting case of this is when a vendor ships a patch for a security vulnerability. Can I do a comparison between the program, say it's some DLL that's getting patched? Can I look at that DLL before and can I look at it after? So even if it's a differential patch and not just like a complete overlay, I can look at the before and after and try to determine what the patch did. Both, did it fix a security vulnerability that may have been unknown, and the vendor didn't say anything about that one? Did the patch install some new DRM code? Just kind of slip it in there, like you got to upgrade your media player for a security vulnerability, and all of a sudden now you can't play awares that you hacked up before. But the really interesting thing is, can I figure out what the details of the vulnerability are just by looking at the patch? The way differential binary analysis works is the graphs that Dildog was talking about, the control flow and the data flow graphs, can be compared before and after. And this is much easier than comparing source code because basically there's a lot of research has gone into comparing graphs. And there are programs out there, open source programs, that you can feed graphs into, and it will tell you exactly, are these graphs the same, or where are the differences in the graphs? Right, things could just be shuffled around. You could be just trying to obfuscate code and just shuffle things around, but if the control flow is essentially just still the same, it's just a bunch of go-tos, the graphs will end up being the same. So when you compare the control flow graphs, right away, it'll highlight those pieces of code that have changed, and you can zero in right on those pieces of code. So the idea is you're going to basically unlink these files down to the individual functions, and then you're going to compare both the call tree of the entire module or process, but then you're also going to compare the graphs within each function. There's 2 papers. If you want more detail on exactly how to go ahead and do this, there's 2 papers out there. One's by Halvar Flake and one's by Todd Sabin. I recommend looking into those. It's eye-opening what you can quickly do from a patch once it's out there. So here's my cheesy graphic. So the idea about discovering vulnerability details from patches, if you could automate that process, that really changes the whole internet threat model. Colonel Boyd, I think it was in the Army, maybe the Air Force, the Air Force, came up with this concept called OODA, Observation, Orientation, Decision, Action. And it's basically the doctrine of modern warfare. And the idea is you have to, obviously more information on the battlefield helps you beat the enemy. But you're basically unstoppable if your loop, where you observe, you orientate that new information to what you already know, you make a decision, and you carry out an action. If you can do those 4 things faster than essentially the enemy can change the situation, basically you always win. So the idea is to make your OODA loop faster than the enemy's OODA loop. And that's basically how modern warfare is conducted these days. So you can apply that theory to basically information warfare. And basically there's a sort of the daily battle out there is vulnerabilities get discovered and vulnerabilities get patched. And there's been a lot of research on. William Arbaugh did a paper a few years ago, and Qualys has been distributing a paper on their research on how quickly things get patched. And it's essentially this sort of a half-life to things getting patched. And I think, was it 30 days was the half-life? So half of the systems are patched in 30 days, and then another half in 60 days, another half in 90 days, and then it kind of tails off for a while, and then eventually actually starts going back up again a little bit. But the idea is if you can quickly determine what the vulnerability is from the patch and build the exploit, then you're always going to have a certain number of machines on the internet that you can control. So this is just basically a fact of the future, is because we're continuously patching systems with technology like differential binary analysis on patches and the ability to quickly create exploits, means that we're always going to be in a situation where a large percentage of the internet is basically owned by, who knows who. And I'm sure the InfoWar guys at the Air Force know this very well. So what are some countermeasures to binary analysis? So the technology's new, but we might as well think about how people are going to try to defeat it, right? So a lot of things like DRM code or license manager code, or code that people really don't want you to know what's going on. The code that they know that you'll take the time to disassemble or poke through with the debugger. What they do to protect the code is they make it self-modifying code. So while the code is running, it's changing itself, and a lot of this is actually using encryption. So the code will be encrypted, and it'll be decrypted on the fly. It'll be as it hits certain blocks of code, it'll, just before it gets to that block of code, it will decrypt that next block, and then re-encrypt it. So even while, of course, on disk it's encrypted, but even in memory, it's encrypted. So this is really going to throw a problem into binary analysis, because essentially the code just looks like random data. So we thought about this problem, and we said, what are we going to do in this situation? And we haven't built this yet, but the idea is to build since the CPU needs to know what the real instruction is at some point, what you do is you build in a journaler, which when the instruction, before it goes to the CPU, basically gets written out to a file, and you essentially journal the program, all this, and you may need hardware to do this, some sort of the software emulates CPU, like Softice kind of thing. Then essentially you're going to have to do things like collapse loops and things back, but you can get you should be able to get the original code back. So the future is bright for binary analysis. Don't worry about self-modifying code. It wouldn't be 2600 or HOPE if we didn't talk about something with the legal system, right? So there is one problem with binary analysis, and that's license agreements. It's a little problem there. Almost all proprietary software, and they thought of this 20 years ago because they knew there's going to be all kinds of ways of poking into the binary, comes with a license agreement which says you cannot disassemble, you cannot decompile, you cannot reverse engineer this software. So what the vendor is saying is, trust us. This binary only does good things. It does things that we told you it did, and it has no security problems in it. If that was the case, there wouldn't really be a problem with those kind of license agreements. But we know reality is extremely divergent from that situation. Almost all software that does anything real, or I'll say all software that does anything real, has security vulnerabilities in it. And all software is probably doing something which you don't know what it's doing, and you might want to for legitimate reasons. So essentially, the way the licensing agreements are written now is you have no right to do a security analysis of a binary in this way. You have no right to know what kind of files the program is modifying. So we need to have basically some laws that allow people to do the kind of inspection on software that they can do on other things in the physical world. But due to the power of software companies, I'm not holding my breath. I think the only way that this would happen is if it could be shown that binary analysis tools actually can help with the security problem. And convincing the U.S. government that they should use these types of tools on all the software they purchase to see what the quantity of security vulnerabilities is, just at least to just get a rough feel for, is this thing written well, or is it written extremely poorly from a security standpoint. I think that's one of the only ways that we're going to get some changes that allow people to inspect software legally. And if that was the case, the next step would be we can actually have software certification labs which could run these types of tools and give you an assay report on a piece of software. Just like you can send your water to some testing agency and they will tell you how much lead you have and do you have poisons in that water. And anyone can do that. Most governments, local governments that have things like well water, test their water regularly. That's the law. But you can test the water too. If you had a way to send a piece of software to a lab and come back with an assay report and say, this program looks like it has 700 buffer overflows in it, 400 format string attacks, it has 3 SQL injection attacks, and by the way, it's listening to the raw network device, and you probably want to know that. Right now there isn't anything like that, and there probably should be. I'm always constantly amazed how we treat software as something completely different than all the other things we know how to do well in society to protect ourselves on a societal level and protect ourselves on an individual level. When it gets to things like proprietary software, the rules are just completely different. Hopefully it will change. Finally, and this is I think pretty far out there, but you have to strive for something. The idea of automatically fixing security vulnerabilities in a binary, where you would decompile the program, analyze it, find the vulnerabilities, and then what you would do is you would have a rule set about how to fix certain classes of problems, automate those fixes, and then recompile the program. I think that creates an order of magnitude problem on top of what we're already doing. But maybe someday you'll be able to do that on software, so you could actually, no matter how poorly the vendor wrote the software, you could fix at least a subset of the problem. A good example would be something like SQL injection. You could just, if you detected that, what you could do is you could just put a call in to do a validator function right before it went to the SQL query, and you could easily patch in a fix there.
One way to think about that, I just thought of this right now, is sort of extending the concept of firewall to software semantics. There are certain, once you have everything in graph form, there are certain patterns that would be considered bad or malicious. Detecting those and not allowing them to run, or fixing them, or changing them, or transforming them away could be thought of as sort of a block rule on a certain type of programming operation. I don't know where I'm going with this, but it's an interesting idea to think of it that way. It's just sort of an abstraction layer above, just looking at data. This is looking at code in that way, in the same way that one might look at data and pass it through a rule set. You could do the very same thing with code. It's all the same once you get the graph. So, yeah, at this point, I would open up the floor for any kind of questions. Anyone would like to, if you want to actually ask a question, come up and to the mic in the middle here and get in line. How much does the software cost? Well, right now we're using it internally as a consulting service. We kind of use it as a robotic exoskeleton for our consultants to make them superhumans. When we get around to making the software public, I'm pretty sure you'll see some numbers on our website in the order of magnitude of 4 or 5 digits, depending on how much money you want to pay us. But as is anything, we have to pay back our research time. So, first question. Yeah, speak a little closer. I don't know if is that on?
Should be.
Hello. Our windows, you do like the pointers areas, pointers.
It's not loud enough. I can't hear.
I'm working on it. Just if you can talk out for a moment.
Go ahead.
I can't quite understand the question. How well does it handle pointers, the program? Okay. There's a component of the system called a range propagator. And a range propagator basically it sees things like the dereference of an expression and says it allows you to query what the value of that pointer is at that point. It kind of walks back through the code and finds what the range is of that pointer. Now, if the pointer happens to be, a constant, like a location on the stack, then that's just a stack variable when you dereference it, and it just turns it into that. Basically, we build these frames, and if pointers are simply pointers, then they're just a variable like any other variable. If they're dereferenced, then you may be making other variables based on them. So we have this generalized concept of layered variables. You start off with registers, and if you dereference that once, you get a frame, which can be a stack frame or a this pointer. If there's a this pointer, then you might get a class out of it. If you dereference that again, then you may be doing things like passing things by reference from one function to another. So, when you ask the question, how does it handle pointers? It handles them like any other variable, and they're just a component of the graph like anything else. But we note that there is a special operation called a dereference, as well as a reference, but that was a little easier. That adds semantics to the system. Anyway, I hope that helps.
Why are we feeding back now?
That's not wireless
Hi. When you were talking about self-modifying code, you said that you weren't worried about that. As far
Talking
as
to the wireless
design
mic?
analysis.
He's talking wireless.
Great.
Thank
It's
you.
working. You said you weren't worried about self-modifying code as to how it related to the future of automated binary analysis.
Yep.
Do you want to talk a little bit about how maybe trusted computing
I think
initiatives,
that mic's a little high.
and whatnot,
It's ringing.
impact on that statement?
Trusted computing effectively adds a hardware component to the software problem of, so that basically, if
Oh, found it?
if one was to do all of the encryption in hardware on an executable, I'm going to come up with a horrible example of a program that cannot be disassembled by anything but the CPU because it's decrypted on let's say the motherboard right before it goes to the CPU. You know, so when you talk about self-modifying, it's basically equivalent to the whole encryption problem. Your question is effectively the same as, what are we going to do about trusted computing in general? And the answer is emulation. Once people can, deduce, what the various public and private keys are and things that are built into the motherboard, emulating that layer, in a system. Effectively, you just need to be able to, get at the CPU and what it's intending to do. If the semantics are completely obscured, then this kind of, binary analysis technique really can't be used. However, insofar that everything that is you can do one way, you can do it another way, you can do the opposite way, as long as it's like as long as you can decrypt the image. I mean, it had to come from somewhere. So it's not necessarily a problem for binary analysis insofar that it's just what do we do about trusted computing in general? How do we get at the bits? So hope that helps. Hey,
What's going on?
what's up, dude?
So two questions. One, with GCC, if you go and throw it like a -06 flag, you're not
Dash
gonna get,
06.
Yeah,
Optimized.
you're not going to get any useful code. I mean, it's kind of here. A lot of times, we crank up the optimization of the compiler, especially GCC.
Sure.
I was wondering if you ever found using these techniques, security problems that are accidentally introduced by compiler or high-level optimization. That's the first one. The second one is a more kind of theoretical question. Has any of your work actually started to run into the boundaries of formal undecidability?
The first question was about the I'm just trying to think of a proper answer. No, I haven't actually seen a compiler introduce a bug, but we've come awfully close. There was a time when we compiled a program with GCC, and the decompiler really threw up hard on it. And it was saying, like this strcpy or whatever is writing way past the end of this buffer. What the heck is going on here? And we're looking at it, and it really just wasn't what the person wrote. We thought it was just a bug in the decompiler. I mean, this thing is, had its fair share of bugs, and maybe it was just our problem. And we stared at it for, it must have been 45 minutes, just staring at it, and we didn't believe that what was decompiled was actually what the person had written in source. But it turned out that due to some very clever pound defines, what was actually being compiled was a lot different than what it looked like. There's some cases, where it's just the human problem, and the compiler itself was not inserting a vulnerability there, but it's something that we just would not have found unless we were using a binary analysis tool. To answer the other question, I didn't actually hear the very end of what you said. Formal what?
Formalize undecidability.
I haven't done a whole lot of research in that area, so I really couldn't tell you. Regardless, I think that's the last question that we have. We just got the red card, so that's 5 minutes. If people want to grab beers with us later, we're not going to talk about this stuff. So, all right, thanks.